So let's look at starter question. Was it starter question number 2 and 3? Yeah. So starter question number 2. So we were asked to factorize, yeah?
Yeah.
So if you can shout what the factorize is, because I can't see it.
3D plus 10D.
Was it 4D square?
Yeah, 4D square minus 100k square.
A square, yeah. So now you need to ask yourself, how can I factorize this? So you can find a common factor if you want. There's 2 ways of doing this. You can find a common factor. So if you were to get 4 outside as your highest common factor, you can get 4 times d square minus 25k square, yeah? So you can say, you can do that. And now, can you notice that you've got d square minus 25k square? So 25 is 5 square and k square. So you've got a difference of
2 squares.
2 squares, and you would just write this as d plus 5k times d minus 5k, and that is fully factorized. Okay, so you could have said, oh, I didn't see that I had 4 coming out, so that means you could have used another route and say, I can see a difference of 2 squares here. That would be 2d minus plus 10k times 2d minus 10k. But that is not finished because you've got 2 and 10, so you need to get 2 out here. D plus 5k. And that is again time 2d minus 5k. And this time you will get your 2 times 2, which is 4, and you should end up with the same answer for both this method or the other method. So I don't know which is the easiest. To me, I would say this is probably easier.
Yeah, I'd say so as well.
But in case you didn't see that you had a highest common factor here between the two, you can still get the answer going through this. Okay, so let's try question 3. So question 3 is to do with fractions. So I've got 1 1/4 divided by 1/2. So what did we say when we divide 2 fractions?
It's not easier if you put it in the same denominator?
Yeah, denominator. Absolutely.
So it was when we were adding or subtracting fractions, in order to do that, we needed to have the same denominator. But when we looked at mixed fractions, we said a good thing would be to change the mixed fraction into what we call an improper fraction. Here it would be, remember, 1 1/4 is the same as 4 times 1 plus this one here.
Yeah, just make it top heavy.
So then that would be 5, yeah, a top heavy fraction, 5/4. And so you can write divided by 1/2. So now whenever you're going to have 2 fractions like this, you can change the divide sign as a multiply. But if you do that, what did we say we needed to do to the second fraction?
Flip it.
Flip it over, yeah. And that would be your answer. Now that you've got to time 2 fractions, you just time the numerators. 5 times 2, which is 10. And then you time the denominator, 4 times 1, which is 4. So I'm not going to leave it like that because I can simplify it. They're both even. So it's the same as 5 divided by 2 by halving them both. Or what you could have done is you could have seen here 2 and 4 I can divide by 2 both, and that would be a 1 here and a 2 there. Okay. So that's how you would do it. You would change first the mixed fraction. But if you had a blank, you need to think about what is 1 1/4. 1 1/4 is 1.25, yeah?
Mhm.
A half is 0.5. Think about you having 1 pizza, yeah?
Yeah.
And a quarter of a pizza. And the question you've been asked is how many halves can you make out of a full pizza and a quarter of it? You've got 1 half here, you've got another half here, and then you've got half of a half. So 2.5. What is 5 over 2? 2.5. So you could draw. If you can't remember any of those rules, guys, don't just stop and say, I can't remember this. Write down what you have. Think about it as something with either rectangles or circles, and ask yourself, dividing by something is to find how many pieces of that something can I put into that number. And then it might become a bit clearer for you. And if this was like a 3 marks and you went through doing this and showing that you were looking and you still get the answer 2.5, you would still get your 3 marks by just putting that and that, because you've understood the problem. You don't have maybe a quick method, but math is about trying to find a solution, and that solution is as good as this solution. Okay, and that's how you should try and read math. You should not try to force yourself into remembering things, because what you've noticed is it's not the easiest thing to remember. Whereas your brain works better when you try to break down a problem. Okay. So we did say we were going to look at volumes of similar solids today. We're going to try and explain how the scale factor applies to 3D volumes. Basically, we looked at linear scale factor, and when we came to area, we said we needed to square it to find the area of the larger of the two. And today, because it's volume is in 3D, area is 2Ds, so 1 to 2, what do you think is going to be? The scaling factor this time is going to have to be cubed. That's the only difference between the area or the volume. Okay. So let's see if we can solve some problem. So if you had the time, you can draw a wee cube, and then you'll be able to see if you've got a cube that is 2 units by 2 units by 2 units. And if I ask you to double the length of each side, and you can tell me how many the volume went from 2 times 2 times 2 to 4 by 4 by 4, which is 64. So if the scale factor is 4 over 2, which is 2, we needed to do scaling factor cube, which is 2 cube, 8, times 2. So 2 times 2 times 2, 8. Times the volume here, 8. So 8 times 8 would have given me the bigger volume. Okay. So another example. We've been asked to work out the volume of each shape and try to link volume and scale factor. So I've got 3 here, 6. So I've got a scaling factor of 6 divided by 3, 2. So it's been doubled. So the first volume is 3 times 2 times 2, which is 12 centimeter cube. Second volume is 6 times 4 times 4. So you do length times breadth times height. Yeah.
Yeah.
And then the connection between the two is your scale factor 6 over 3 So again, that's a linear scale factor, the line equal 2. Now, if I do 2 cube times 12 centimeter cube, which was the first small one, will give me 8 times 12, which is 96. So that's exactly what we did with a small cube there. So the type of question you can get asked during an exam would be that I've got, given that the two boxes are similar, calculate the volume of the large box. So straight away, if I see volume and large, you should be thinking, I'm looking for an ESF here. I'm going bigger. I need to enlarge. Okay, so ESF means the longer side divided by the shorter side. So 6 divided by 2 is 3. Because we're going into volume, the first one was 15 millimeter. We said to go from one volume to the other, we need to cube our scaling factor. So 3 cube is 3 times 3 times 3, which is 27 times 15. So if it's a non-calculator, you could do 27 times 10, which is 270, plus half of 270, which is the 27 times 5. Okay, and the total should give you 405 milliliter. So a volume, have you noticed we've not given them into with centimeter cube, we're using here liters or milliliters, okay? So we've looked at that before. Another example, we've got a diagram here. We've been shown 2 jugs. We've been told straight away they are mathematically similar. So this only works if they are similar. The volume of the smaller is 0.8. Find the volume of the larger. So again, ESF 30 divided by 20, which is 3/2, 1.5. So we do 3/2 cube times 0.8 liter. And that gives me 27 divided by 8 times 0.8. So 0.8 divided by 8 is the same as 8 divided by 80, or 0.1, then you get your 2.7. So 0.1 times 27 is 2.7 liter. And that is plausible, because if you think about a 30 centimeters, just a ruler, a jug that is 30 centimeter in height would contain about 2.5, 2.7 liters. Okay. So in this exercise here, what we've been asked is to write down the ratio of the sides of the super duper, which is the big, and the super duper medium. So you've got a big size. Oh, sorry, super duper and big. So this is the question we've been asked to find. The first one is the ratio between them two. So that would be 16. So you would write 16. The ratio is just 16 and 12, right? Like that. So 16, 12 in ratio. And then you could simplify that as 16 divided by 4 is 4. 12 divided by 4 is 3. That's why you've got that ratio. Super duper and big is a ratio of 4/3. And we've been asked to do the same for the super duper and the medium. So 12 divided by 10 or 6. Sorry, super duper again. Yeah, 16 divided by 10. So 16 by 10, which is 8/5. Yeah. Super duper, so the big one, the bigger of the bigger one. Now that we've got what we've been asked to find, is we are looking for areas here. So the super duper box needs 1,600 centimeters square of cardboard. How much will the big box need? So it's going to be less. because it's less, we're looking for a reducing scaling factor. So if it's 4 by 3, the reducing is just going to be 3 over 4. Or you can say it's going to be 12 divided by 16, which will simplify to 3 by 4. And once you've got that, because you're looking at area, you need to square that time 1,600, and your answer would be 900 centimeters square. Okay, so area, you need to find scaling factor. You square it first before timing the bigger of the area here to reduce that. Now the big one holds 2,700 centimeter cubes. So now they've told us we're looking at volumes here. The big one, which is this one. How much will the medium one hold? So the medium one should be less. Yeah. So reducing scaling factor would be 10 over 12. So 10 divided by 12 is the same as 5 divided by 6. And because we're talking about volume, the volume for the smaller of the two is going to be 5 over 6 cubed times 2,700. And if you plug that in your calculator, you should get 1,562.5 centimeter cube. So I've not checked, but I think you can just put 1 decimal place in case there was more than that. They've not asked us. Okay, so that's how you do volume. In this example here, we've got two sides of cornetos. The small one costs 40p. What should the big one cost? Again, it's not just about the length that will decide what the cost is. It's what you're going to put inside that. So which is a volume. So because you're going to put ice cream in it, you are talking volume. So they've not told us that, but we need to think outside the box, even if it's what's going to be inside it, to know that they are checking for us to see if we know that this is a volume that matters, okay? So to go to the big one, we're going to look for the ESF, which is 12 divided by 8, and simplified is 3 divided by 2. So technically, the small one should cost 3 divided by 2 cube time how much you've paid for the small one, 40p. And 3 divided by 2 cube times 40p is 27 divided by 8 times 40, which is £1.35. Okay, so that's how you would get your mark here. They're trying to see if you know the volume scaling factors. Yeah. Okay, so I think let's have a look here. The ratio of the volume of two spheres is one is 10 times bigger than the other in terms of volume. Now, what is the ratio of their surface area? So to do that, what you would need to do is find first the scaling factor. So we know that scaling factor cube is 10 over 1, which is the enlargement scaling factor. That is 10. Now, if you were to look for the linear scaling factor first before doing the surface area, you would say to yourself that the scaling factor is cube root. So if SF cube equal 10, then SF is cube root of 10. And if you plug that in your calculator, you will find 2.1544. Now, to find the ratio for the surface area, because we're talking about surface now, you're going to have to do what you find SF, put that square, and this time you will get 2.1544 square, and you calculate that, you get 4.64. So that's your ratio, and they've asked us to answer to 1 decimal place. So if this small, if the big ball is 10 times bigger than the small ball in terms of volume, in terms of area, the big ball is 4.6 times bigger than the small one. That's basically what it is. So the ratio of the surface area, because they've asked us to write it into this form here, is just 1 4.6 to 1 decimal place, because that's what they've asked us to do here. Give your answer to 1 decimal place. So it's another way of showing you that you can go from volume now to surface, surface to linear, back and forth, okay? But these would be the harder questions when it comes to doing similarity. You don't see them coming often. Okay, and for your homework part 1, when it comes to volume in terms of similarity, so you would need to try exercise 22b, question 3 and question 5. So a couple of questions, page 245. And obviously, if there's a part 1, there'll be a part 2 coming. So the part 1 is the easiest one, which is some of the exercise we had a look at. When you find the scaling factor, then you cube it to get the answer. Whereas part 2 is the couple of harder ones, just to make sure that you're okay with that. Is that taken? Yeah?
Yeah.
And for part 2, it's just 22C, page 248. And this time is question 1, 2, and 3. Okay. And that should conclude. So they'll be here basically.
Mm-hmm.
2 bottles, if you go to the large one, find the ESF, give your answer here. So we're talking about volume here. If the volume of the small is 250, then ESF, you cube that, time by 250, again boxes. So if you go for the area of the small box, you need to find the reducing scaling factor, cube that, time that by the large box. And for 22C, you've got more of a problem. The piece card will make a tube 9 centimeter long. And then the third question, we've got the volume of 2 canisters. The height of the small one is a certain height. Calculate the height of the large canister. So if you can work on those, then that means you should be okay with any similarity type questions. Okay, now that you know what a scaling factor is, you can use that quite a lot in real life, to be honest. There's a lot of things where people do modeling for one part to another. And so just stop at those questions up to 3. After that, if you want to practice more, I've just put some past paper type questions. So you don't have to do them. Those after those 3s are just past paper questions. Okay, and that concludes the chapter on similarity. So I'm going to stop recording here and we'll make a different video for the next lesson.